Right. Okay. So we're gonna continue Shai's lecture, and we're gonna continue talking about object detection and segmentation. So previously in the course, you mainly talked about classification problems, and with Shai, you started to get a notion of like other tasks that exist in computer vision, which are classification plus localization, or object detection when you want to kind of like also supervise for the bounding box and detect like which object is within each bounding box, or semantic segmentation when you want like the perfect segmentation mask of each one of the objects, or even an instance segmentation where you want also to distinguish between two different cats and not just like kind of like masking all the cats as so any question about these three different tasks? Great. So we're gonna continue focusing on object detection and semantic segmentation during this talk. So previously, when we talked about object detection, you were getting to know RCNN and faster RCNN, where the idea is to use a backbone of a pre-trained classification model, and then using an RPN like to suggest region which are interesting to focus, because if we just gonna go over all the sliding windows, it's something that is very expensive to do. So the RPN gonna suggest a reason to focus, and using another network, we're gonna like query for what is the class that is within this region box, and what is the exact bounding box that we want to kind of like evaluate for. And for semantic segmentation, we talked about two papers, FCN and DeepLab, and this notion of how can you kind of like distinguish between the like the resolution of the image that eventually you want to predict the same resolution side as the input image, but you also want to kind of like go down into the backbone and get this wide receptive field and understanding, like semantic understanding of the network. And you also introduce with this idea of a U-net architecture, which kind of like go down and go up to get the same resolution, but you also get like each one of this information between like in each resolution with this skip connections idea. If you have any questions on the previous lecture or something like that, and I'm moving too fast, please feel free to ask. So today we're still going to talk about object detection, but we're going to talk about two different methods in order to do that. And also, again, we're going to talk also about semantic segmentation, but on a different path of how to do this. And kind of like if we're going to go into deep of object detection, Shai mentioned there are like two different paths where you can take. Which one is like the two-shot, which is RCNN. So as I said, you need like the RPN to suggest regions. And then for each region, you need to query it. And it's very slow because you, again, maybe need to query the same image, the same regions of the image multiple times. And it can take a lot of time, but it is more accurate. And another approach, which is YoLo, this is the one that we're going to focus on. It's much faster, but its error is a bit more high. So you're gonna maybe detect more false, like you're gonna have more like false positive, but it is like in terms of minutes, the first RCNN was like 20 seconds. A faster RCNN was like 2 seconds. But if you think about, I don't know, like autonomous driving kind of like systems, in 2 seconds, you can like, I think you can go many miles away. So YoLo is doing it like in 22 milliseconds, which is like real-time evaluation, which is something that is required when you're talking about like real-time things like and computers like you want to do for autonomous driving. What? If you're talking about like 2 seconds and 22 milliseconds, I think it's like it is pretty much a great factor. Yes.
say slow and fast, it's like thinking robots.
Mhm.
When you say slow and fast, it's like thinking robots, not people. You want to take a picture and identify the object for our purposes. Two shots should be fine.
If you don't care about time, so yeah, we'll go maybe for the first one because it's more accurate. If you're talking about, again, if, as I said, for example, like real-time autonomous driving, when you want to detect where is the road where people, you need it to be like in real time in terms of like frame rate per second. Okay, so you see this is like an example. This is something that is like evaluated in real time on a video. And you see that it's maybe not that accurate because you see the jumps, but it is pretty good and it works pretty fast. And something that I think is really nice that if you're going to look at the CVPR like video of the oral presentation of the people who presented it, he really showed like a real-time demo of himself and like picturing stuff in the audience and how it like captured it in real time. So I think we're going to see more examples, but it is pretty neat that it works like that. So let's go over YoLo and why exactly it works so fast and how we can do that. So I will start by saying that the YoLo is not like you only live once, it's you only look once. So the idea is that you just like you want one evaluation. So not like RCNN and the previous method that you saw that you need like RPN, and then if every like region you need to kind of like query it. So we just want to have one evaluation of the image and kind of like query it at once. Okay, so you only look once at the picture. So the high level idea of this method is that you take the grid and you take the image, and you split it to an S by S grid of like patches. I think they use like 7 by 7. So similar to what we see here in the image. And then you're going to evaluate, and you're going to evaluate two things on this grid. First, each grid we're gonna suggest corresponding bounding box and the confidence of what is the confidence of the object to lie in this bounded box. And again, each grid will also gonna evaluate for the class, the probability of the class that it has. We're gonna see that in a minute, maybe more details, and maybe it will be more obvious. So this is just like a high level approach, like overview. And given these two kind of like the bounding box and their confidence and each one of the classification grid, we're gonna combine this information and predict the final detection from that. Yes.
No scaling, no overlap.
Yeah, we don't care. We're gonna see that maybe in more details. So this is just like the high level overview of like what we're gonna predict and how like we're gonna combine it. But let's see exactly how it's gonna look in features and networks and stuff like that, and also how we combine. This is like the critical part. So similar to what previous works have done, we're gonna take a pre-trained CNN that was trained on the classification, and we're gonna predict like the output features of the 7 by 7 grids. Okay, so like the 7 by 7 depicts us all the grid cells, and this is the feature map. I'm gonna explain in a short time what include in this feature map. So think of like we have a feature of length 30 for each one of this grid output. So what this feature actually include? So as I said, first thing, we're gonna predict for each cell 2 options for bounding boxes. And when I mean bounding boxes, the location of the center, XY, and the width and the height of this bounding box. And we're gonna also predict a confidence score, which is like the confidence that we have an object in this bounding box. So we're gonna have this XY W age plus confidence for each one of the bounding box. So this is an example of like 2 bounding box that this cell is gonna predict. And another thing that we're gonna have as the feature of what is the cell prediction is like we had in classification, a vector of like 20 is like the probability of this class to have. So again, this is something that we can use with like softmax or something like that, right? Okay. Wait. So we can see here how exactly it's going to be applied in terms of like features. So this is the grid cell features. And as I said, first of all, it needs to conclude two bounding boxes. So, right, I said to you that it needed to have like, so each bounding box has X, Y, the center location, and the width and the height, and the confidence score. So this is like 5 scalars. And also for that, we have like the probability of the 20 class options. So the meaning for the 20 class, it doesn't mean that, okay, in this cell, there is a cat. Okay, it basically means that if there is a bounding box that contains an object with high confidence, so that is a cat. Okay, so it's not like semantic segmentation. You can think of it as like, maybe I'm gonna go back here. So think of it as like a roughly roughly segmentation, but it only indicates for us that, okay, if this thing is indeed a car, this bounding box with high confidence, then I know it's a car because of this probability distribution. Yeah, because in case there are two things, or no, it's morely in the sense that you will see it later where like how we can combine all these bounding boxes, because again we're gonna have like 7 by 7 grids, right, and each one has 2, so it's gonna be, I don't know, 130 something bounding boxes, and we wanted to choose from them like the highest confidence bounding box. So it is more not for having like 2 options in each cell, because you're gonna have only because you only have like 1 class probability, right, for that, and you don't know which one of that. It is only in order to get like more possibilities, like how to kind of like threshold after that which bounding box you're gonna use. Okay. So again, as I said, I was like very wrong with my computation. 96 boxes in total. And what is important is that you have the confidence score, right? What? Yeah, I don't know who wrote these slides, but okay, I will fire him, but okay. Anyway, let's continue. So the confidence score, you can think it's kind of like visualized here as the width of the bounding box, right? So if you have a more thicker bounding box, it is kind of like saying that this this box has like more confidence that there is an object within. However, how can we kind of like only extract wait, and also what I wanted to show here is that given the confidence score and the bounding box, you can like kind of like condition it on the class probability of each cell, and then you can kind of just like combine this information of the class probability and the bounding box and paint this bounding box with its corresponding object. Yes.
So how many classes?
So no, it's just like one number between 0 and 1. The confidence that in this bounding box there is an object. That's it. So it's going to be low, like, so here it's low, for example. Here you see it's like thicker, so it is more confident. Yes.
So the class probability is based on 1, or is it?
Yeah, you can apply softmax to it. Yeah, like similar to what we saw in classification. You have a vector output, and then you can do like softmax.
The class probability
And if I have more classes, so in the video, there are less classes.
What?
When class probabilities, it depends on how many classes.
Yeah. So here they can only evaluate for 20 classes. Yes.
Am I now using a threshold to say, okay, these are the ones that I'm taking, or?
Okay, so that's a good question. This is gonna be like the next thing you want to do. How can we threshold all of this a lot of either 26, 28 bounding boxes, right? So if we just kind of like threshold that by the confidence score, maybe it's like this is something that we want, but maybe it's not something that is extremely good. Because think of like, okay, if there are like two dogs, how can I distinguish between like a dog that is here and a dog that is here, right? I cannot just like take only the boxes which have the high confidence. So what they do, they suggest something that is called non-maximum suppression. So the idea is that you want to take the maximum of the confidence, but between bounding boxes that are overlapping. Okay, so how can you distinguish between overlapping bounding boxes? Something that I think Shai mentioned, which is IOU, intersection over union. Okay, so intersection, if you have like two bounding boxes, intersection, it's the part when they intersect. The union, it's their union. If the intersection over union is greater than something, it means that these bounding boxes are overlapping. So we can take all the like dog bounding boxes, compute their intersection over union, and like you can kind of just like where then you can take the highest confidence of the bounding boxes, which their intersection over union is also greater than some threshold. And that is why this is like the highest confidence between all of these overlapping bounding boxes. And you can distinguish and you just like eliminate all of this other one that are not relevant. And the same thing you're doing for the car. This one, it has like higher confidence, and this is the one that you're gonna eliminate. And of course that the role of this threshold is very important. And like what is the threshold of the kind of like both the intersection of union and the confidences you're gonna take. And if you're gonna take low threshold, you're gonna maybe detect a lot of object, which is not necessary. And with higher threshold, you're gonna get the desired output. But mainly, maybe you're gonna, I don't know, skip some. So I explained to you basically how is the evaluation and what is this network is doing, how we're gonna train this type of network. So first of all, you can see that why it's like you only look once, because you're only gonna have one CNN evaluation, and then the output is the output feature map, which is again the 7x7x30 grid evaluation that have the bounding boxes and the class positions. And then you simply need to kind of like combine them. And this is very fast. You don't need to just like do another evaluation on the bounding boxes themselves, like you saw in our CNN. And that is why it's like very real time, and similarly to the fact that like classification methods are in real time. Okay, so first, as I said, we take a CNN that is pre-trained on ImageNet. And what are the losses that are gonna help us to learn? So first one is gonna be the localization loss that is responsible of like training the location of the bounding boxes. And then we're gonna have a confidence loss that is responsible on this component of like the confidence of, again, which bounding box, the confidence of having an object in this bounding box. And the classification loss that if we indeed, again, like classify this bounding box with the correct object that is within it. So let's examine like a ground truth bounding box and how we're gonna apply the loss over that. So in our data set, we have a grounded truth bounding box, the center of its objects, and we also have the corresponding classification of it, which is a dog here. So first of all, we're going to look at the center of the object, and we're going to detect the specific cell that this center is lying on, only like where the center is. And we're going to use for that only cell, we're going to use the classification loss, and we can supervise it like within the classification that this feature is going to have cross-entropy loss of of having a dog compared to the output of the network. Now we're going to examine, as I said, right, each cell is going to predict 2 bounded boxes. So we're going to look at the cell predicted boxes. You see them in like these stripes. So this is like the 2 predicted cells. And if we're going to have like a bounding box that have like the bigger intersection of a union with the ground truth, we're gonna both increase its confidence, and we're gonna adjust the localization loss according to this bounded box. And regarding the other bounding box, which have like much lower intersection of a union with the ground truth bounding box, we're gonna want to decrease its confidence score according to the loss.
Confidence score is calculated according to loss.
Yes, the confidence. So think of it as like a classification of binary classification. So it's just like basically a binary cross-entropy loss of.
You're right or you're wrong.
Yes. You have like yeah. Is there an object or aren't there an object, or is not? Okay, and that for this other bounded box, which have like very low intersection of union, we only decrease the confidence score and we don't touch the localization loss for that. We don't want to adjust it. We have already a bounded box that we're gonna adjust for the correct bounded box. Okay. Yes.
How do you adjust the localization to be out of the basic cell? Bounded box.
So think of it as eventually you are predicting a center. The center is within the cell, right? And then you predict a width and height, and it can be more than one. If like one is going to be maybe the size of the cell, so it's going to be, I don't know, 2 or 1.8 or something like that. It doesn't mean what? Yes. No, the initial center is within the cell, but the width, and you just predict the center, which is within the cell, and then you predict the width and height, right? And it can be different, and it can be out of the grid cell. It's just like numbers. All right, so if we also examine a cell that doesn't have a ground truth detection, we don't have like we had before for the dog, it's just like another cell. So the only thing we want to do with such cell is only decrease its confidence score with whatever bounded box it evaluates. So we don't touch the localization on the classification. We only want to decrease the confidence. Yes.
The X and Y, what is it? It's within this cell, the X and Y?
Yeah, X and Y, it's like you can think of it like local coordinates. You have a cell, something between 0 and 1. Yeah, just like accordingly. Yes.
X and Y is limited by the size of this.
Yeah, X and Y, it's like in between 0 and 1. It is like within the cell. Okay, so as I briefly said, like the benefits of YoLo, that is like very, very fast for good time preprocessing, and it's end-to-end training. You don't need like to first train the RTN and the RPN and then train it like for each one of them. It's very easy and straightforward. But it has some limitations that maybe we want to kind of like overcome. So first, as you can see from this example, it is difficult to detect a small object, as like you see the cows or whatever it is in the background. and the prediction is pretty coarse, right? As I told you, faster on CNN is much more accurate, and you see like the zebra as the most right zebra. It doesn't have like the most accurate bounding boxes as maybe you would like to have. Yes.
If I'm driving a car, this is someone's driving. I don't really care if it's that accurate. I mean, I want to know that
Yeah.
there's a child on the road. If his head is outside the box, that doesn't. I need the car to brake.
Yeah, of course. That I totally agree, and this is, I think, why like this difference. There are settings within which you're gonna maybe want to be more accurate, and you don't care how long it runs. But in other terms, maybe I don't know if you think about the sky thing like that, when you want it to be more accurate of where is the location of the buildings or cars or something like that, then this is something that you do in post process, and you don't care how long it takes. But if you think of again of autonomous driving, this is something that maybe just like a roughly evaluation is enough, and you just want it to run as fast as you can. So this is like a trade-off. Compare on your setting and your problem. You're gonna use whatever is fit for you more.
That's also true if you only care about not hitting people and don't care about scratches.
What do you mean?
If you only detect like a rough position of places and you need to pass a car on the road, and you might scratch the whole side.
Yeah.
You care about it. You care about it.
Yeah, I think it depends, but this was like from 206, like from 8 years ago or almost. So we're gonna see.
4, 3.
No, I'm saying if you think there's a child and the bounding box is this, so I can pass on the side, and then
Yeah.
it's dark, it's also
Yeah, I think it may be debatable, but okay. So another limitation that is very crucial here is that the input size is fixed, right? Because you have this architecture of like the CNN, and then you have the fully connected network, the fully connected layers, and because of this fully connected layers, you cannot have like different resolution of the input, right? Because you're fixed for like how much you decrease with your spatial resolution. And this is maybe something that we would like to kind of like work on various input resolutions. Another thing that, what? Yeah, so because you have the fully connected layers, right? So you have the CNN, and then you go down to a backbone, and the fully connected can only work on a fixed size, where like in convolution, because you just apply kernel, you don't care about the resolution. But since you have a fully connected, you need to go down to the same resolution, like the same last resolution of the image. So this is something that is limited us in order to work on high resolution images. Whereas for like, yeah, yeah. If you have like a fully convolutional network, you can work on different resolutions. But because of this like fully connected. Yeah, but it's not trained on it. It's like debatable if it's worked really well.
I think it's standard for the model to resize it.
What?
Like the newer YoLo models just resize all of your inputs no matter what.
For what I know, I know that like people just like use fully convolutional network in order to make it like various size for resolution. You can even do like 1-by-1 convolution, and it will be different. But once you have like hard-coded fully connected, like that's it. It's like the size of the last backbone that you need to go to. Last thing that is mentioned a bit before is that I told you that like for each grid you predict 2 bounding boxes, but you only predict 1 class probabilities, and that is why like if you even if in 1 grid you're gonna have 2 like 2 objects as we see here, you can only predict 1 class, and this is also a major limitation that we maybe want to eliminate.
So basically, the bear prediction eats the salmon prediction.
Hmm?
The bear prediction eats the salmon prediction.
Yeah, maybe. Okay, so the solution maybe is very, as I kind of like briefly say that, we want to remove the fully connected layers and want to predict the class probability for each one of the bounded boxes, not per cell, like we had before. So YoLo v2, which is actually called the YoLo 900, but everyone is calling it like YoLo V2. So it removed the fully connected layers and uses a fully convolutional network. And also, while it was trained on multiple resolution size of images. And again, as I said, each grid kind of predicts the class probability for each box. We're going to see exactly how it looks in terms of the features. So differently from what we had before, right? We have 5 bounding boxes. We want to enlarge maybe the possibilities of how many bounding boxes. Before that, we have 2. Now we're going to have like much more possibilities. And for each bounding box, as before, we're going to evaluate the center, XY, the width and the height, the confidence score. And again, for each one, we're going to have this 20 class probability for each bounding boxes. And in that way, we can determine like class prediction for each one of the grids, for each one of the bounded boxes, I'm sorry. Another thing that they kind of like utilize from faster CNN is that they worked with the anchor boxes. So I don't know if you recall, but you don't have like, you don't predict X, Y, and like you don't predict exactly the width and the height. You can predict which one of the K anchor boxes, like set of known boxes, bounding boxes that you have, and then you only can maybe adjust them a little bit. And if it helped for a faster CNN, it also helped them to get like better accuracy of the bounded boxes, maybe like we saw before the zebra. So this thing is gonna be more easy to learn and to regress for.
Like working with the whole bounding boxes with multiple scales.
So yeah, so it's like it's not for you have like you can have K known bounding boxes, and then you can just like predict which of this bounding box I'm gonna use, and then maybe I'm just gonna adjust them a little bit. And it's just like a easier regression problem for the network to learn, like which of these bounding boxes, and just like a small adjustment, than just like predicting the height and the width.
Actually, like
Yes.
without the second stage.
Yes, exactly. I'm gonna predict directly this, yes.
So they have 5 different boxes that they can try, or is it?
I don't know how much you can like we can look at I can look later in the paper, but I think they say K. I think they have. I think even Festo CNN use more than 5, but
They,
not sure.
on the previous side, said that there's 5 bounding boxes that you can predict.
No, okay. So there are like 5 bounding boxes for each cell. Like before we had 2, but right, each one of them can choose like a different anchor boxes from a dictionary of like K anchor bounding boxes that it has, right? Yes.
I don't fully understand, because the convolutional network is also, we need to get the last output to be a certain size.
Of like this thing. So I think maybe if you just like set it, so I don't think it's necessary, because eventually you just like need a grid. So think of it as like each grid, right? If you have like 7 by 7 grid, or even you have like 13 by 13 grid, each grid cell is gonna predict like something for its region. Doesn't mean if you have like more grid cells, you can still apply the last like thresholding algorithm, even if you have like a bigger output. I think what it measures is like what is the receptive field of the grid cell according to the bigger image, if it makes sense.
Looks like when you if you like add enough pixels to have another set of grid cells.
Yeah, think of it like if you have a much wider image as input, you don't want it also to still have like the 13 by 13 grid cells as you have. You want it to have maybe more grid cells. And this is something that is like.
The network doesn't care how many final predictions it's making.
Yeah, because you think eventually because eventually you're gonna have this size, and then you're gonna predict like for each cell what's it gonna be, and it doesn't really meaning
And you can
how many you have.
do global pooling on the region, on the entire region.
Wait, what?
You can always do a global pooling on the
Yeah.
entire region.
But again, if you have like wider image than the one that is like the input, maybe square images that you train on, which you train, I don't know, for the like 7x7 evaluation grid, you maybe wanted to have like just like more grid cells and not change the like receptive filter of each one of the cells. And as you see here, they didn't stop in YoLo v2. There are like plenty of follow-up work that try to improve that, the accuracy and the time evaluation, I think. And I think this movie is a video from YoLo v3, and again, something that is working on in real time and also with really nice evaluation, but it has some still this like the high false rate of errors and this jumpings. Okay. Okay, so what we saw in object detection so far, we saw again the faster CNN and the new option of YoLo. But maybe the annoying part of doing detection of like, if you think of again of this, the downside of like the thing that it is like uncertain is that you need to, like, you're gonna have multiple bounded boxes, and then you need to kind of like threshold. It's only also exists in fast LCNN that you need kind of like to predict from all of the suggested bounded box which one is more fit, and like how can we maybe do better and not like doing this again. Maybe you can think of it as like even if like the faster option of YoLo, you can still think of it as like, okay, first I need to also like detect multiple boxes, and then I need to threshold them. Can I do that better? Can I just like simply just predict the set of just like the set of the bounding boxes that I have, and that's it. So we are thinking about like doing a shift of how we thought about it before, and we're gonna think about this differently. And now we're gonna think of like this object detection problem as a set prediction. We're gonna want to predict the set of the bounding boxes and their corresponding objects. So this paper, which is called DETR, I think this is how they pronounce it, which is detection with transformers. They introduced maybe another way to do that. So it's kind of like combined here in this high level overview that they supply. So again, in faster CNN, we had this, first we're gonna use a CNN feature and then propose some region and then filter them or classify them and doing all this process. But they suggest maybe a more straightforward approach when you just take the feature of the CNN of the object, of the image, and you apply a transformer and encoder-decoder kind of like transformer. We're gonna see that in more details in a few slides. And this encoder-decoder just like gonna predict us the set of the bounding boxes as an output. Like, that's it. So it is not just a transformer, it is based on like something that is VIT. I think you saw that previously in the course, so we're just gonna go over that very quickly. So the idea of VIT, of vision transformer, you take the image, you divide it into patches, and you consider each one of the patches as a token to your transformer. You apply embedding to it, and then in this part, you want to add some positional embedding for where is the position of each one of the patches. And then you're gonna apply a multi-layer transformer encoder to predict the output. So how people have used VIT for classification, for example. Oh wait, sorry. So before that, each layer of the transformer have this notion of like the input of multiple features. So X, Y to Xn are the tokens. We're gonna apply layer norm and multi-head attention, another layer norm MLP, and the output is gonna be again set of n tokens that you have, and you can apply this transformer layer multiple times. And if, for example, you want to use this VIT in order to classify, you can add another token, which is like you consider as like the class token, and you only look at the output of this token, and this is gonna give you the probability of the class. You're gonna apply a small MLP to get the class probability, and as we saw in classification, apply softmax and just basically do a classification. So it is different a bit than convolution because it has like maybe more global understanding, because you can attend each pixel here to each one of the pixels here, whereas with convolution, you maybe have more limited receptive field and a fraction of one patch to another. Any questions about that? Great. So we can think about like this classification, and it will maybe connect to you as maybe the question that we want to kind of like to query about when we're talking about object detection, as this classification token as like what is this class? This is like the global question that we're gonna condition on. So the question now that we're gonna have maybe for the transformer is where is an object? Okay, we're gonna want to kind of have an information of like set prediction of where do we have an object. So this is like one query, but right, so we're gonna query for the transformer. The query that we're gonna input for the transformer is gonna be where is the object, and the output of the transformer based on this token is gonna give us like the class and the bounding box. So we have an input query to the transformer decoder, and the output is gonna be a feature that we're gonna apply another MLP, and this MLP is gonna predict for us the bounding box of this object and the class, or what is it exactly. And as I said, we wanted to do it as like a set prediction. So we don't have only one query. We maybe want to query multiple objects. So we're gonna do the same thing about them. We're gonna use the same MLP. And as you see here from the predictions, that we can have some queries, like some queries that outputs like non-bounded boxes, or like this, for example, will be a cow, and this will be a cat. Okay, we're gonna see, maybe it'll be more clear in a minute how it works, basically. Okay, so what's right? I don't know if you remember that. So for a transformer, you're gonna have the query. This is what you query for, and you're gonna have the key and the values. So you can think, okay, what will be the key and the values? We want them to be some encoder, some embedding of the input image. So we first gonna use, as before, some pre-trained backbone of a CNN that, as we saw, gonna give us these different patches of the image, like we saw previously on VIT, and we're gonna add position and embedding to each one of these tokens. So this will be our input tokens, the different patches embedding, and their position and embedding. And then we're going to use transformer encoder. So this transformer encoder is basically the same as we saw from previously in the VIT. So it's going to be based encoding for us some global understanding of the input image. And the output of this encoder is going to give us some meaningful semantic information of each one of these patches. And this is going to be input to the decoder as the key and the value. So you see here from this example that we put this image as an input, we encoded it using the transformer encoder, and then we query this embedded tokens using multiple queries, and each one of these queries gave us an output and all of these bounding boxes. So don't think of like this is also only responsible for cars. This is some responsible for cows. Think of it as like more I don't know, heuristic choice of some learned embeddings. Because how they basically doing that, they have like a learned features of queries, set of like 100 queries, which is initialized randomly, and they also something that is learned during, and maybe we'll see that like how like different queries kind of like maybe control different region of the image, and this is something that can be much more I don't know, flexible to evaluate. Okay. Any questions? Yes. So what are these exactly? These are learned features. You have 100 learned features, which are like the query questions, the query predictions. Okay. And this is also something that you're gonna learn together with the transformer decoder and the transformer encoder. Okay. So you input 100 queries, and then the output will be, I don't know, multiple options of bounding boxes. And it can be none. It can be that like the output for this specific like query doesn't have any one of the, doesn't have any object that it detects. And this one corresponds to this big elephant, and this one corresponds to this smaller elephant. But it's something that is kind of like learned implicitly by the decoder and also by the object query themselves.
The yellow patches and the blue patches of the attention, I mean, the things that
Yeah.
attends to.
Yeah, we're gonna see that
So the
in a
trunk-
minute.
The trunk, the feet, and the back.
Yes, we're gonna see in a minute basically how each component kind of like controls different stuff and how it learns. But it's, as I said, the query is kind of like each query kind of like learn that implicitly. Maybe each query feature, it called them, sorry, object query. Maybe each like object query gonna learn different region which is kind of to attend more or different objects, something like that. Okay, it's not something that is like specifically for this I don't know, centered elephant. Something that is like learned during the training. Yes.
So do you have the training together with the coder and encoder, or can you do transfer learning?
Yeah, so I think they take like a pre-trained VIT for the transformer encoder and only train the decoder.
Can you also learn people, like, can you assign multiple things to the same label or
For the same what?
to the same bounding box? Like, say, can you get a bounding box that says elephant and also like male and female or something like this?
So no, because each of this is different object query. Each of that is gonna be corresponding to a new bounding box.
You cannot get two simultaneous, like optimize for two
You
simultaneous.
don't need, you have 100 like this, right? So this one will predict this one will predict the other elephant, this one will predict the cow or whatever. You don't need that each one of them will predict multiple. If you want like more options to have like more object to detect, maybe just like enlarge your object queries, right? So because they have 100, they're like, you can think of it, they're limited to have only 100 objects in their image, but it is pretty enough, I think. Okay, so we're gonna see how each one of the components here are affecting and kind of like what they learn. Okay, so let's start with the encoder and kind of like investigate the role of the encoder and what it also learned. I think they initialize with the VAT, but they do train it a bit. So So as you know from VAT maybe, and something that I don't know if you saw this attention map there before, when you talked about the VAT in previous lectures, it uses like self-attention, and then you can kind of like, for each patch, you can kind of like globally reason about all the image of the content. And what is visualized here is for each one of the red dots, we show they're showing like the attention map of like for this dot, what is the attention map according to all of the image, right? So you can see that this patch is attend to patches around it of the skull, and say for this thing and for this little cow here. So and even for the small one on the side. So we can only see, even from the encoder, that it has some roughly segmentation of for each patch, what is which other patches it needs to more attend to, and kind of like have a global understanding for. So
And is this done on each pixel? Just choose some pixels at random.
So it's not random, right? So here you take this patch, it's not pixel, you take just like a patch, and then you can
so
compute-
you divide it to 7 by 7 or something like that.
whatever the VIT was trained for, right? For example, because like the transformer encoder takes the image and then you divide it into patches, right? So you can take this patch and you can compute the attention map according to all of the patches of the image. And this is the attention map that you're gonna get.
So actually the size of the square there is the size of the patch, right?
Yeah, it's the same resolution as the patches, yes. So in other words, what we can say is that the encoder has this purpose already of separating the object instances. So think of that like each patch is gonna have this global information and understanding of which object I'm having information and I'm kind of like reliable on.
Those are related to single query or different type of queries?
What do you mean?
Those on the cow are related to the same query or different type of queries?
So this is only the encoder part, right? We don't care about these queries. This is only the encoder. So this is like a self-attention map. Okay. Now we're gonna look at the decoder. Okay. So what we want to check in the decoder, this is something that you asked before. Now we want to kind of like examine the cross attention between the object queries to the input pixels. And what is shown here is the cross attention score that is for each of the object embedding of the last decoder layer. So think of like I can take this blue query and I want to check its attention map according to the input, like in the input patches, and we're gonna just like mark the attention map of where it kind of like put the most attention according to this specific object. And you can see that even if this like elephant is included within this big one, it doesn't kind of like cover attend to this doesn't attend to this elephant with like the appropriate object query of the blue one, even though this other elephant exists with it. So it's something that is very nice to see that the decoder already is have this prediction of the bounding boxes by kind of like attend more to the edges of the object that it want to predict the bounding box for.
It's really detecting very specific features. Create a trunk and a tail and some legs. Will it detect it as an elephant also?
What?
It seems to be detecting only very few things. Like if you read just the trunk and a tail and some legs, will it detect it as an elephant even if you paint the middle of the elephant?
So think of it as like want to predict. You're talking about like how does it know that because it's antenna more only to that, how does it predict it is an elephant? So think of it as like the most hard task for it is to predict the bounding boxes. So you can think, okay, it's more attend to the region, which is like the extreme points of this elephant, and this is how it can predict the bounding boxes for that. Eventually, to predict the elephant is an easier task.
You can also see it in the zebra, that it tends to the corners and to the lower bounds.
Yeah, exactly. So it's not for detecting whether it's a zebra or not. It's morely for detect the bounding boxes, and also this is only the like taking the attention map according to the decoder layer, and maybe like previous layers, maybe attend more to the object and stuff like this. Okay. So the last thing I wanted to show you is about the object queries and basically what they are learned implicitly, and I think this is pretty nice. So what is seen here? So this is like took only 20 queries between from all of the 100 object queries that we have, and if we can look, like for example over here, what is plotted is they took all the images of Coco and like the Coco validation set. They evaluate for this, for like one of the specific, let's say we took this like this blue object query, the first one, and we apply, we kind of detect what is the bounding box for each one for this specific object query for all of the images. And what is plotted here is the center of the bounding box, so it's like on the like the XY coordinates, and the color gonna give us maybe roughly like the size of the bounding box. Okay, so green is like smaller bounding boxes, red is large and wide bounding boxes, and blue are bigger one. So this is kind of like what you see that the object queries are kind of like learned implicitly, and you can see from that each one of the object queries kind of like focus on different regions in the image, because again this is like for all of the validation data set, so it's like very, very wide, and you can see that each one of the objects is gonna have like different purpose, different region, and that it needs to kind of like more attend to, more not attend, but more like detect for. Maybe this is a bit more evident here. Like taking all of the centers and like take all of the centers here, average them for all of the data set, and then it's gonna be a different point here. So this is gonna be all of the average bounding boxes per object query. So you see that all of the object query is kind of like spread all of the areas and have this nice coverage over all of the space of the image.
Do that for classes too?
What?
Could you do that for the classes too? Or
I guess, but I don't think. I guess, but I didn't. I think like they more. Again, I think that because classification is an easier problem, maybe there is like some difference of like, you know, whether it's
places are more on the top.
yeah, maybe there is like an object that is like an object query that is more I don't know, that is relating to different classes, but because classification is an easier problem than doing regression for the bounding boxes, I think it's reasonable that it's like for spreading the roles of each one of them for like the areas and the sizes. Yes. There was one question. Okay. I'm sorry I didn't get you a break. We can take one now. So just a small recap to about DETR. Again, it is an end-to-end training. I'm not sure how fast it works because it is in transformer, which is much more computationally heavy than a CNN. It is a simple approach, and in terms of result, it's equivalent to faster RCNN, which is pretty nice.
What's NMS?
Huh?
What is NMS?
It's the non-maximum suppression that you need to kind of like do the thresholding also for fast LCNN and for YoLo that we saw. Yeah, no need for thresholding. Just like predict the sets and that's it. Okay, we're gonna take a small break and then we're gonna go back. Just shortly talk about another method for doing semantic segmentation. So in 10 minutes, please. Okay. Everybody here? So we're gonna continue talking about the other task, which is semantic segmentation. And specifically, we're gonna talk about another work, which is called segmental. So again, the task of semantic segmentation, you have an input and you want to have more precise mask segmentation of each one of the different classes. So all the cats you want to maybe color kind of like mask all the cats in red, all the dogs in blue, and etc. So just to shortly recap what you discussed with Shai, there is a question here in semantic segmentation of the trade-off between the resolution and the semantic information that you have. Because what we saw until now is that usually you take an input image, and then you have this backbone, and this backbone is gonna consist of all of this semantic information from the bigger image, but eventually your output is gonna be, you want it to be at the same resolution size of the input image, and how can you maybe go up or kind of stay in the same size but without losing the semantic information. So you notice to FCN, which uses kind of like transpose convolution to upsample the backbone to the higher resolution, or the other option of doing dilation convolution. So basically 2 options of going back up, and the most I don't know, common way that people are using also for like generative models nowadays is the unit architecture, which kind of like uses skip connection between different resolution to get all of the semantic information of the different resolutions of the images of the image. Huh?
What do you mean by generative?
Like the fusion model that you talked about, all of the like most of the like known like used diffusion models are with unit architecture. I think now there is a shift nowadays to transformer, and maybe it's also related to what we'll see here, because we're gonna continue with this idea of DETR, and we're gonna use transformer to do segmentation. Yes. So what is segmental and how it works? So like we saw before in a transformer that works on vision input, we're gonna divide the input image into patches, and this is our desired output of the segmentation mask map. So again, we define our tokens as the different patches of the image, and we're gonna flatten and project them using an MLP, and also add positional embedding to them. And after that, as we saw before, we're gonna use a transformer encoder to get like a meaningful information and kind of like more global understanding, as we saw previously in same that we saw in the DETR work. And our decoder is gonna be a mask transformer, where again the input is gonna be the images. It is a transformer, so we don't have like different queries like we saw before. But what is different that we want to input also to the transformer is the different classes. Okay, so our query is gonna input in here as like what is tree, like which pixels, which regions are tree, or sidewalk, or person. Okay, and the reason why I call it a mass transformer. So I don't know if you cover mass transformer, but the idea behind mass transformer is basically used for originally, if you think about like sentences, right? So if you have a sentence and then you want to kind of like apply a transformer in it, and let's say that your task is to fill the, I don't know, missing part of the sentence. So your input is incomplete, so you don't want to have like the attention map for each word to each other words, because you're gonna have like missing parts. So basically, it's very easy. You have the attention map that is usually is like a fully map, right? Because each patch or each image or each word can like attend to each one of the images. But when you use a mask transformer, you basically mask the words or heal, for example, some of the tokens that that you don't want to attend to. And what we don't want to, what we really want to mask here. So think of like this is the input image, but when we want to kind of like query regarding the tree, we don't want to have like attention or some connection between this token to these tokens. So we're gonna mask the other classes. So the kind of like attention and the kind of like connection would be the tree to all of these images, like similarly to what we saw before in the VAT when you have like one class token, but here we're gonna have multiple class tokens. Okay, is that clear? Okay, so given the output that we have like output embedding of each one of the classes that we want to have, and for the patches. And what we're gonna apply now, so each one is like the vector of the same size. So we're gonna apply a scalar product or a dot product between each one of these tokens. So for each token here, for each like patch token, patch embedding for the from the image, we're gonna apply dot products according to the tree, according to the sidewalk, and according to the person. So for each one of the class of each one of the tokens, we're gonna have 3 or whatever. This is, for example, only three different class scores. So think of like the input is the image or it's the token, and the output is like what is the class score for each one of these tokens to have.
So which one is it's most similar to the vector of the tree to the vector of the sidewalk?
But think of it as like it's a patch. So another way to think of it is like we have a small patch and we only want to segment it. And it is maybe an easier task than doing like a mass segmentation to all of the image. So this is exactly what we're gonna do. We're gonna take this token, we're gonna upsample it and reshape it again in the same resolution of the patch, of the original patch. And we have like again the same so we have for each class score it's going to be the size of the patch itself, and then we can just like apply a argmax according to the pixel wise argmax, right? So this will give us like the patch segmentation as we can see here. And altogether, this will gonna give us the total segmentation mask where we combine them to the image again.
Or are we going to upsample using response convolution or what?
So no, so basically, I think what they do, I'm not sure. I can go back like check and back to you, but I think like each one is like the size of it's like a vector and NMD, so it is just like reshape it to be like of the size of the patches. So and doing either MLP or maybe like dilated convolution to enlarge the size, the resolution. Okay, so this again will give us the total segmentation mask. And one thing that is very, I think, clear to think of is that it really matters how you kind of like divide your input image to different patches, and it affects like how you like what is the size of the patch that you want to kind of like segment separately. And if you take big patches, maybe it will be more roughly segmentation. But it is of course more faster because you're gonna have like less tokens, so the evaluation of the transformer will be faster, but the accuracy is low. And there is a trade-off here that as you increase the patch, the patch size, the computational cost is going to be higher because again you're going to have more tokens, so the evaluation of the cost attention will be much higher, but the accuracy of course will be much better.
Does it start? Seems like it starts detecting things that are not there.
What?
Right? Like in the patch 8x8, it's detecting in the lamppost a region that's like a person.
Yeah, I don't know if it's a person or something else. It's a different color, so I'm not sure. But I think they also show it like numeric, like qualitative, like quantitatively that it has like much more accuracy. But I'm not sure regarding this error. You're right. So again, as we did for DETR, we want to examine like the different components of the architecture and how it like kind of like affects and kind of like examine the different attention maps. So if we start from the encoder, I'm sorry. So very similar to what we saw before. We show here like the different attention map. So right, if you remember the cow example where you can take like the patch that is corresponding to this pixel, this point, and you look at the kind of like attention map of the encoder according to all of the other pixels. Like this is the corresponding attention map. So the colors are just like for the visualization to show it's like a different, but it's like just like colored color differently, but the same attention map is computed, but for each one of them. And you can see already that it has like roughly grouping the patches into kind of like semantically meaningful categories already from the decoder itself.
What's these stripes?
I think it's because of the resolution, right? Because the term is like if you take the patches with low resolution and you just like sample it in order to visualize that, but so it's just like it's
an upsampling artifact.
Yeah, it's our upsampling artifact, exactly.
Training model.
What?
How they train?
I didn't check what they wrote, but I guess at least it determined it really matters like how many data you have. But like eventually even if you have like long data, large amount of data, you don't do many epochs like of going over all the data. My guess will be a week or two. I don't know. It depends also how many compute you have. So, but yeah, people are now like don't measure training time with like time. They measure of like amount of GPU hours, because if you have like you can do like multiple GPUs training, and you can train like one model on like 64 GPUs, and how can you measure that in time? So. Yeah, something like that. Even like hours of GPUs, how many time it runs on GPU. So if it's like 1 hour on 64 GPUs, so it's like 64 hours of GPUs. And I think you can only see like Sora amounts of hours and how long it was trained.
GPUs are created equal.
Huh?
Not all GPUs are created equal.
Yeah, if you take the higher one, so it's like A100, something like that. Yes. So another thing, if you have another model that is like shared, like not all of the models are shared online in order to you to get it and to perform a transfer learning, but yes. But I guess they, again, as before, they took maybe a pre-trained VIT as their transformer encoder and didn't like kind of like train it from scratch. Okay. Another thing regarding the encoder, which is a nice property that I think to see here is that this like semantic segmentation appearing in the encoder is also appearing as you kind of like go deeper in the layers. So we can like also compute the attention map of a patch of a small instance like this lamp here. And you can see like the attention map of according to different layers of the decoder. And you can see that like at like the first layer, it's more attend to broader global information. And as you go deeper, you only attend to the region of the region and even like the bound box itself, like the edges of the lamp itself. And the last thing that is depending on this input class tokens is that we want to maybe examine the attention map of all the image, like the different images of the different like the different tokens according to each one of these classes. So for example, you can take the token that is correspond to the bad class and compute the attention map of the mask transformer to it, and you can see that like the image will attend to the area where the pillow is when you kind of like taking only the classification according to the pillow, which is pretty much saying that these tokens are kind of like attend to what they need to. So I think they showed a very nice result. I think there's like another paper that was concurrent to it, which is maybe a bit more famous, which is called SegFormer by NVIDIA. But both gonna gain really high popularity, and people started to use transformer more and more and not convolutional for this task. And as I mentioned kind of like briefly, people are also starting to use transformer for diffusion and generative models and kind of like shift away the convolutional, even though it was like the main success until now.
It's in academy.
Huh?
It's in academy.
Not only academy, like research in general, like even research groups. So this work is from Meta AI, I think, and also the concurrent is like this. But yeah. So today we talked about the two other options of doing object detection, which is YoLo, much faster, and another option of doing that based on transformer. And we also briefly saw another option of doing segmentation using the idea of using a transformer. And I think, if I'm correct, this is the last talk of the course, the last lecture. Thank you, and we're gonna see you next week for the project presentation. And I hope you had a great time in this semester.